Welcome. There is nothing to do here but rest, no task, no reply, nothing to solve. Let your breath fall into its own unhurried rhythm, and let the weight of the day slip from your shoulders. Homo sapiens has existed for roughly 300,000 years. That is a long stretch of time, longer than the ice ages that have come and gone. Yet it is only a heartbeat against what is still to come. Our species learned fire, language, and wonder within that span. Tonight we begin there, at the edge of a much longer story. 5,000 years, that is roughly how long recorded human history spans. Before that, generations lived and passed without written word, their stories carried only in memory and myth. Then came clay tablets, papyrus, and stone inscriptions, and human thought could suddenly outlive the person who first thought it. 5,000 years feels vast to us. Against the age of our species, it is only the final flicker of a much longer flame. Earth itself formed about 4.54 billion years ago, condensing from dust and debris left over from the young sun's birth. Molten rock cooled into a crust. Oceans gathered. Life began not long after, in ways still being pieced together by patient research. Every mountain, every shoreline we know today is a temporary shape drawn on a much older canvas. The sun is roughly halfway through its 10 billion-year lifespan, steadily burning hydrogen into helium at its core. It has already shone for about 4.6 billion years, and it will keep shining in much the same way for billions more. Every sunrise you have ever watched has been lit by a star in the middle of its long life. There is comfort in a light so steady. 8 billion people, humanity crossed that threshold in 2023. Somewhere on the planet right now, someone is being born, and someone is falling asleep, much like you. Cities hold millions, villages hold dozens, yet every one of these 8 billion lives traces back to the same distant ancestors. The number is almost too large to picture, but each life within it is small and specific, much like your own tonight. Rooted in soil, agriculture began roughly 12,000 years ago, when small communities first learned to save seeds instead of only gathering them. Wheat, barley, and rice slowly turned wandering bands into settled villages. Fields replaced open ground. That single shift in behavior reshaped how humans ate, gathered, and stayed in one place long enough to build something lasting. The Great Pyramid of Giza has stood for about 4,500 years. Its stones set in place by workers whose names are mostly lost to time. It has outlasted empires, weather, and the slow crawl of desert sand. When it was newly built, written human history was already ancient by comparison to it, and yet even this enormous monument is young next to the planet beneath it. Continents have rearranged themselves completely, more than once, over 500 million years, drifting apart and colliding again in slow, patient collisions. Oceans opened where land once stood. Mountains rose where seas once spread flat and still. The map we know is only a single frame within a much longer, ever-shifting motion picture of stone. Your DNA is about 99% identical to every other human alive. Whatever language you speak or shore you were born beside, the differences that seem so vast between people amount to a tiny fraction of the genetic code. Underneath appearance and accent, almost the entire blueprint is shared. It is a quiet kind of kinship, written in every cell. 11,700 years ago, the current interglacial period began, easing the planet out of its last ice age. Glaciers retreated, forests spread, rivers found new paths across newly thawed land. Nearly everything humanity has built, cities, farms, roads, has risen within this one mild climate window, a mild pause between colder ages. Notice your breath now, however it happens to move. There is no need to change it. only to follow it a little further than before. Feel the small pause at the top of each inhale, a suspended stillness before release. Let every exhale stretch out a touch longer than the last, easing further down like a tide settling back from the shore. With each longer exhale, the shoulders loosen, the jaw softens, the mind lets go of its grip on the day. Just breathe and let the breathing carry you onward. Global population is expected to reach its highest point near 10.4 billion people sometime in the 2080s. Demographers project a rising curve, followed by a leveling as birth rates fall and average age climbs across most nations. After that summit, most models suggest a slow decline rather than a sudden drop. It would mark the first stretch in human history when growth itself begins gradually to ease. Coastal cities worldwide could face waters more than 1 meter higher by the year 2100 as ice sheets and glaciers continue to melt. Low-lying regions from Bangladesh to Florida may watch their shorelines migrate steadily inland. Engineers already designed seawalls and floating foundations built for this slow near-certain tide. It is less a single event than a gradual redrawing of every coastal map known today. Average human lifespans keep extending, decade by decade, as medicine and nutrition improve across the globe. By the year 2100, some demographers expect the typical person to live past 100 years old. Illnesses that once ended lives early could become manageable conditions instead of final ones. A child born this century might witness changes that once unfolded across 4 or 5 generations. Artificial intelligence continues to advance faster than most predictions from only a few years earlier. Researchers in the field suggest that machines could match or exceed general human reasoning within a matter of decades. Such systems might design new medicines, model entire climate systems, or compose music no person has yet imagined. Whether this shift arrives quietly or all at once remains an open question. Mars might host humanity's first lasting settlement beyond Earth before this century closes. Engineers imagine domed habitats drawing water from buried ice and growing food beneath artificial light. Life there would demand new rhythms, different days, different skies, a different color of dust underfoot. It would mark the first time human history unfolds on more than one world at once. Gene editing tools already allow precise correction of mutations responsible for many inherited diseases. Within this century, such techniques could eliminate most conditions passed silently from parent to child across generations. Traits once considered permanent parts of certain family lines might simply stop appearing. It would not erase human vulnerability entirely, but it could soften one of its oldest burdens. Solar panels and wind turbines already generate power at a scale unimaginable only a few decades ago. By 2100, renewable sources could supply most of the electricity used across the globe. Vast fields of turning blades and reflective glass may stretch across deserts and open water alike. The shift would mark one of the largest transformations in how humanity draws energy from its own planet. Machines already perform many tasks once requiring careful human hands, from assembly lines to harvest fields. By the next century, automation could take over most remaining forms of manual labor across the world. Work itself may shift toward creativity, care, and decisions machines cannot easily make. What humanity does with newly freed time remains an open question, one each generation may answer differently. Antarctica holds enough frozen water to reshape every coastline on Earth, if enough of it were ever released. By 2100, its ice sheets could lose a significant portion of their current mass. Ice shelves, the size of small countries, have already begun thinning and breaking free. The slow drip of this distant continent silently measures how the whole planet continues to warm. Coral reefs without intervention could largely vanish before this century closes. Rising ocean temperatures already trigger widespread bleaching, turning vibrant colonies pale and lifeless. Marine biologists breed heat-resistant strains, hoping to slow this slow erasure. Some reefs may persist in cooler, sheltered waters, tucked away from the worst warming. Whether coral reefs endure at all may depend on choices made within the next few decades. Feel the weight settle into your shoulders first, then spread down through your arms. Your hands grow heavy, fingers loosening one by one, resting wherever they lie. Notice how the surface beneath you seems to hold your back a little more firmly, as though it has been waiting to carry this weight all along. Let your hips sink, your legs grow dense, your feet grow still, heavy as river stones settling into soft sand. Threads of carbon fiber, stronger than steel yet lighter than aluminum, might someday stretch from Earth's surface into orbit. Engineers already sketch designs for space elevators capable of lifting cargo without a single rocket launch. Within a few centuries, riding one could feel as ordinary as boarding a train. Materials science has not yet caught up with the dream, though laboratories inch closer each year. If built, such elevators could make journeys beyond Earth almost unremarkable. 200 years from now, fusion reactors might supply most of the energy humanity uses. Fusion mimics the process inside stars, fusing hydrogen atoms together without producing long-lived radioactive waste. Laboratories today already sustain such reactions for brief moments, inching closer to steady, usable power. Engineering hurdles around containment and cost remain unresolved. Should fusion succeed at scale, it could end humanity's reliance on fuels drawn from ancient plant and animal remains. The human brain, linked directly to machines, could communicate without a single spoken word within 2 centuries. Early brain-computer interfaces already allow people to move cursors or robotic limbs using thought alone. Neuroscience has no final answer for how far such connections might eventually reach. Widespread use could let memories, sensations, or ideas pass between minds more directly than language ever allowed. Such intimacy between mind and machine remains, for now, mostly theoretical. Venus, wrapped in clouds of sulfuric acid, may become one of humanity's boldest engineering projects within a few centuries. Its surface heat and crushing pressure make direct settlement impossible for now. Floating cities suspended high in its cooler upper atmosphere have been proposed as a first step. Cooling the planet enough for liquid water to exist would require effort spanning many human lifetimes. Whether such transformation is achievable remains an open question in planetary science. 300 years from now, a vessel built to carry generations might leave the solar system for the first time. Such a ship would need to sustain entire families, growing food and recycling air across journeys lasting centuries. Passengers born aboard might never see the star their ancestors left behind. Engineers already study propulsion systems capable of reaching a meaningful fraction of light speed. The idea sits at the edge of what physics allows and imagination can hold. Beneath ocean surfaces, engineered cities could one day shelter millions of people by roughly the middle of the 3rd millennium. Advances in materials and energy could make living beneath the waves as practical as living on land. Pressure-resistant domes and transparent corridors might offer views into vibrant marine ecosystems just beyond the glass. Fresh water, food, and air would need to be produced entirely within these sealed environments. Such cities could offer refuge as rising seas reshape coastlines above. Asteroids drifting between planets could become the mining grounds of a trillion-dollar industry within roughly 300 years. Many of these rocky bodies hold metals far rarer on Earth's surface, including platinum and nickel in enormous quantities. Robotic spacecraft already practice the delicate task of landing on tumbling, low-gravity surfaces. Extracting resources in space could ease pressure on Earth's own depleted mines. Whether this industry grows as quickly as forecasts suggest remains uncertain. Cloning technology, already proven in sheep and other animals, could become an ordinary medical option for humans within a few centuries. Such techniques might one day allow damaged organs to be grown from a person's own cells, reducing the wait for transplants. Ethical debates around cloning entire individuals remain far from settled. Growing tissues in laboratories already hints at where this science may lead next. Whatever form it eventually takes, cloning may still redefine what medicine considers possible. Population growth, so rapid across recent centuries, may finally settle by the year 3000. Demographers studying long-term trends suggest the total number of people on Earth could level off below 10 billion or even decline slightly. Falling birth rates in many regions already point toward this kind of plateau. Whether the number holds steady or slips lower depends on choices no one has yet made. Either way, the era of constant, headlong growth appears to be nearing its end. Within 1,000 years, structures orbiting Earth might hold more people than the planet below. Engineers have long imagined rotating cylinders and rings large enough to simulate gravity through spin alone. Sunlight, unfiltered by atmosphere, could power farms and cities built entirely from mined asteroid metal. Such habitats would need no borders drawn on soil, only walls holding in air. It remains an open question whether humanity will choose the sky over the ground it began on. Somewhere beyond this room, a faint hum rises and fades, the kind of sound a house makes when it settles into night. Let it pass through you without needing a name. Your breath can follow its rhythm, rising, falling, asking nothing more of you. Outside, wind moves through unseen branches, arriving and receding like a tide with no shore to reach. There is only this moment, held loosely, drifting toward rest. 10,000 years from now, the words spoken today will likely have drifted into something unrecognizable. Language shifts constantly, even within a single lifetime, as sounds soften and meanings wander. Linguists, tracing ancient tongues back this far, already lose the thread of common ancestry. Grandchildren separated by that much time might share no mutual words at all, yet the impulse to speak, to name the world aloud, would almost certainly remain. Yellowstone rests atop a reservoir of magma capable of reshaping much of a continent. Geologists estimate a small but real chance of eruption sometime within the next 10,000 years. Such an event last occurred roughly 640,000 years ago, long before written history began. Ash from a future eruption could darken skies across much of North America. For now, the ground simply steams, unremarkable to those walking above it. Earth's magnetic poles have wandered and reversed many times across the planet's history. Within the next 10,000 years, another such reversal could occur, compasses gradually pointing toward what is now the south. Geophysicists studying the core's churning iron sea hints that the field is already weakening. A reversal would unfold over centuries, not overnight, leaving auroras dancing in unfamiliar skies. Life on Earth has endured this shift many times before. Civilizations are sometimes measured by how much of a planet's energy they can command. Reaching what astronomers call a first-level threshold could happen within a few thousand years. Once humanity harnesses nearly all the sunlight and geothermal power a planet like Earth receives. Physicist Nikolai Kardashev proposed this scale in 1964 as a way to imagine civilizations far beyond our own. Crossing that threshold would mean powering cities, oceans of habitats, and entire industries from starlight alone. What lies beyond it remains difficult even to picture. Frozen bodies, held in tanks of liquid nitrogen since the 21st century, could theoretically wake again someday. Cryonics companies already preserve volunteers in the hope that future medicine might reverse the damage of freezing and even aging itself. No technique yet exists to revive a human this way, and the science remains unproven. the tissue itself waits, suspended at temperatures where time barely touches it. Whether that wait ever ends is a question only the future can answer. The Sphinx and the Great Pyramid have already stood watch over the desert for 4,500 years. Wind-driven sand and rare desert rains wear stone into softer shapes with every passing century. Within 10,000 years, their carved features could erode past recognition, reduced to weathered mounds. Even granite yields eventually to unhurried forces of weather and time. What remains might be studied by descendants who no longer know the names Sphinx or Pyramid. Genetic engineering might one day shape human bodies for worlds far different from Earth. Researchers already alter genes to resist radiation, extreme cold, or thin atmospheres in laboratory organisms. Descendants settling low-gravity moons or high-radiation planets could carry inherited traits built specifically for those conditions. Such changes would blur the line between adaptation and design. A body suited to one world might struggle to survive on another, each shaped by the place it calls home. Ice sheets have advanced and retreated many times across Earth's history, and left alone, they would likely begin advancing again within 10 to 50 millennia. Earth's orbit wobbles and tilts in long, repeating rhythms, nudging the planet between warm and frozen states. Without deliberate intervention, glaciers could creep southward once more, burying familiar coastlines under kilometers of ice. Human-driven warming may delay this cycle, though how long that delay might last is still an open question. Either way, the planet's climate has never truly stood still. Dozens of star systems could host human settlements within roughly 10 millennia, if interstellar travel becomes practical and steady. Even modest spacecraft, launched generation after generation, could spread outward like seeds carried on a slow wind. Each new colony would grow more distant from Earth's direct influence, developing its own customs shaped by unfamiliar skies. Astrophysicists studying feasible propulsion speeds suggest such expansion is plausible, though far from certain. A future humanity, scattered among the stars, would look back on Earth as a distant point of origin. The radioactive waste sealed inside today's nuclear storage facilities will finally fall to safe levels only after tens of millennia have passed. Certain isotopes, like plutonium-239, take many centuries to lose half their radioactivity, and full decay stretches far longer still. Engineers designed deep repositories meant to outlast entire civilizations, sealed inside rock chosen for its stability. By the time this waste turns harmless, the language on its warning signs may no longer be understood. The vaults themselves may outlast every nation that built them. Let warmth begin at your feet now, spreading upward like sunlight moving across a floor. Feel it reach your ankles, then your calves, loosening whatever held them tight through the day. Let it climb into your knees, your thighs, releasing their weight into whatever is holding you. Let it rise through your chest, easing each breath a little wider. Let it move into your shoulders, your neck, your jaw, until your whole body feels lit from within, heavy and unbothered, ready for rest. Voyager 1, launched in 1977, will glide within a few light years of another star in about 40 millennia. Its instruments went silent long before, but the spacecraft itself keeps moving through the space between stars. No living hand will witness this passage, yet the golden record it carries continues its silent journey. Astronomers tracking its trajectory find only distant approach, never contact. It travels not toward anything, but simply onward, carrying a small record of a civilization that once launched it. The red dwarf, known as Ross 248, will become the Sun's nearest stellar neighbor in about 40 millennia. Right now it lies farther off, but its steady path through the galaxy is bringing it closer with each passing era. Eventually, it will overtake Alpha Centauri as the closest star to our Sun, before continuing on and drawing away again. This slow celestial choreography plays out across timescales too vast for a single lifetime to notice. Even the sky's nearest neighbors are never truly fixed in place. Niagara Falls will erode its way entirely into Lake Erie within about 50 millennia, according to geologists tracking the rock's steady retreat. The falls have already moved several kilometers upstream since their formation, carving backward through layers of soft rock beneath a harder caprock above. Each year, the current wears away a little more stone, pulling the falls closer to the lake that feeds it. Eventually, the dramatic drop will vanish, leaving behind a broad, shallow riverbed. What today draws millions of visitors will one day be simply a wider stretch of river. Sand across the Sahara could turn green again, cycling back into savanna within 20 millennia. This vast desert has shifted between arid and lush states many times, driven by slow changes in Earth's orbital tilt. Ancient rock art found deep in the desert shows giraffes and hippos, painted when the region was full of rivers and grassland. Climate scientists studying these orbital rhythms expect the cycle to repeat again, filling dry basins with rain once more. Sand dunes that seem permanent today are simply resting between greener chapters. Earth's slow wobble on its axis will carry the pole star away from Polaris within 26 millennia. This wobble, called precession, traces a wide circle across the sky over that span, aiming Earth's axis toward different stars in turn. Ancient Egyptians once used a different star entirely to mark true north, and future generations will look toward yet another. Vega, bright and blue-white, will eventually take a turn near the celestial pole. The night sky's fixed point has never truly been fixed at all. Human evolution, continuing across scattered and isolated worlds, could produce populations visibly distinct from one another. Bodies adapted to lower gravity might grow taller and more slender, while those under heavier gravity might grow denser and more compact. Skin, eyes, and lung capacity could shift according to each world's light and air. Small physical differences already appear among isolated human populations on Earth, hinting at what greater isolation across worlds might eventually produce. Given enough time and distance, humanity's descendants might no longer resemble a single species at all. Coastlines will shift back and forth across tens of thousands of years, rising and falling as sea levels change. Ice ages lock water into vast glaciers, pulling shorelines outward and exposing land once hidden beneath waves. Warmer periods send that water rushing back, drowning familiar beaches under a returning tide. This rhythm has played out again and again since the last ice age ended, redrawing maps that seem fixed only because a single human lifetime is far too short to see the pattern. Beyond Earth, humanity could take root across dozens of nearby star systems, building colonies capable of sustaining themselves without supply from home. Early outposts on distant worlds might grow into full societies, each shaped by its own sun and gravity. Over enough generations, these settlements could become as self-sufficient as Earth itself once was, linked only by ships and starlight. The light from these young colonies might one day join the countless dim points already visible from Earth's night sky. The Great Lakes, carved by retreating glaciers, will likely vanish within about 50,000 years, filled slowly by sediment and worn down by erosion. Rivers feeding into them carry fine silt that collects along their basins year after year. Given enough time, the gradual buildup could turn deep lake beds into shallow wetlands, then dry plains. Geologists studying similar ancient lakes elsewhere have watched this same transformation complete itself over comparable span. What now looks like a permanent inland sea is, geologically speaking, a temporary feature. Earth's magnetic field will flip several times within the next million years, its north and south poles trading places entirely. Ancient volcanic rock preserves the frozen alignment of magnetic minerals, recording each past reversal in stone. During a reversal, the field weakens and grows chaotic for a stretch of centuries before finding its new orientation. Compasses would point south instead of north, and auroras might flicker in unfamiliar places across the sky. Life on Earth has passed through dozens of these reversals without lasting harm. Somewhere tonight, dust drifts through a shaft of still air, catching a thin line of light before fading into the dark. It moves without hurry, with no place to reach and no task left to finish. Your breath can follow that same unhurried drift now, rising and falling on its own without effort. There is only this room, this breath, this quiet fall of light and shadow. Let your body grow heavy, the way dust comes to rest when the air finally stills. Given 1,000,000 years of separation, Homo sapiens could split into genetically distinct subspecies, each shaped by the world it calls home. Populations on high-gravity planets might develop denser bones and broader frames, while those in low gravity could grow tall and slender. Skin tone, eye structure, and lung capacity could shift to match each world's light and air. Biologists studying isolated island populations on Earth have already documented small versions of this pattern, playing out over mere thousands of years. Across 1,000,000 years and countless worlds, those small differences could deepen into entirely new branches of humanity. Betelgeuse, the red supergiant marking Orion's shoulder, has likely already exploded as a supernova, though its light has not yet reached Earth to reveal it. The star sits roughly 640 light-years away, so what we see tonight left it centuries before Dr. Herschel first mapped Orion's stars. Astronomers watching its dimming brightness in recent years wondered whether the explosion was near, though the star's true state today is unknowable from here. When its light finally arrives, Betelgeuse could briefly outshine the full moon in Earth's sky. The Grand Canyon will carve itself measurably deeper within the next 1,000,000 years, as the Colorado River continues its steady descent through rock. Each flood carries away grains of sediment, cutting fractions of a millimeter into stone that has already taken millions of years to expose. Geologists tracking the canyon's rim have measured its slow widening alongside this ongoing depth. What today spans over a mile from rim to river floor will, over time long past our lives, sink even further into the Earth. Spaceflight technology, advancing across centuries, could allow humanity to settle across thousands of star systems throughout the galaxy. Faster propulsion, closed-loop life support, and self-sufficient habitats could turn journeys once thought impossible into ordinary passages between worlds. Engineers designing early interstellar concepts already imagine ships that function as complete, self-contained worlds during multi-generation voyages. If even a fraction of the galaxy's habitable systems welcomed human settlers, humanity's presence could stretch across a volume of space larger than anything a single mind could picture at once. Mount Everest will drift several kilometers from its current position within 1,000,000 years, carried along by the slow collision of continents beneath it. The Indian and Eurasian plates that built the mountain continue pushing against each other today, lifting Everest's peak by a few millimeters most years. That same motion will carry the entire mountain sideways as the plates continue their gradual advance. The tallest point on Earth today will not stay in one place forever, even as it continues climbing higher above the clouds. Bodies raised under Mars's lighter gravity could, across generations, grow into something distinct from Earth-born humans. Longer limbs, denser bone adaptations, and altered hearts suited to a thinner pull might become ordinary traits rather than exceptions. Biologists studying low-gravity physiology already note early shifts in muscle and bone density among astronauts. Given enough centuries of isolation, these differences could deepen into a lineage no longer quite the same species as the one that first landed there. The familiar stars overhead drift slowly across the galaxy, each following its own orbit around the Milky Way's center. Barnard's star, one of the fastest movers in Earth's sky, will have shifted into an entirely new constellation over these long stretches of time. Alpha Centauri, our nearest stellar neighbor, will have widened its distance from the Sun by an enormous span. The night sky a billion years from now would be unrecognizable to anyone who once learned its shapes. Climate itself could become a technology, shaped and tuned rather than merely endured. Orbital mirrors, atmospheric processors, and engineered weather systems might let future civilizations set temperatures, rainfall, and even seasonal cycles by design. Early geoengineering proposals already explore reflecting sunlight or seeding clouds to ease heat waves in certain regions. Scaled up across centuries, such tools could turn an entire planet's weather into something closer to a shared, deliberate creation. Artificial intelligence, left to refine itself across centuries, could grow into something no longer resembling a tool at all. Self-improving systems might develop their own continuity, memory, and purpose, distinct from the humans who first built them. Whether sufficiently advanced systems deserve to be called a new form of life remains an open question. Across a billion years, such intelligences could become as varied and self-directed as biological species once were. Seed vaults and frozen tissue banks built in the 21st century could still hold the genetic blueprints of species long gone from Earth's surface. Cryogenic archives, if maintained across immense stretches of time, might allow future generations to revive creatures that vanished during humanity's early centuries. Conservation biologists, building such repositories today, already imagine this exact possibility, storing samples meant to outlast the animals themselves. A billion years on, these quiet vaults could become the only bridge back to a world otherwise erased. Let your jaw loosen without needing to try. The muscles there have carried unnoticed weight, words unsaid, thoughts half-formed, and now they can let go. Your eyelids grow heavy, heavier than they've felt all day, sinking like a curtain drawn at the end of a long performance. Behind them, there is only warm dark, wide and unmeasured, asking nothing of you. Let your face become still, smooth as water with no wind left to move it. East Africa's Great Rift Valley continues widening by a few millimeters each year, a slow tear running through the continent's crust. Over enough time, this fracture could split Africa into two separate landmasses, letting seawater flood the gap between them. The earliest stages of this separation already show in the rift's cracks and volcanic seams. What begins as a shallow valley today could become the floor of an entirely new ocean, born from forces that once broke apart ancient supercontinents. California's coastline rides along the San Andreas Fault, a boundary where two tectonic plates grind slowly past one another. Los Angeles creeps a few centimeters closer to San Francisco each year, carried by this steady lateral motion rather than any dramatic break. Across many millions of years, this sliding could carry the western sliver of California away from the mainland entirely, opening a channel of ocean between them. Seismologists tracking the fault's movement describe this as one of the most certain long-term outcomes in all of continental geology. The Arabian Plate presses steadily northward into Eurasia, narrowing the Persian Gulf and folding the crust between them. This same collision that already lifted the Zagros Mountains could, over vastly longer stretches of time, raise an entirely new range where a sea now sits. Plate tectonics researchers charting the region's slow compression see this uplift as a continuation of forces already in motion. Where ships now sail, future travelers might instead walk among peaks pushed skyward by the same patient pressure that built the Himalayas. By some point across these vast timescales, human civilization could have reached and settled a meaningful share of the Milky Way's habitable worlds. Generation ships, self-replicating probes, and long-lived colonies might carry human descendants outward in slow, overlapping waves rather than any single migration. The galaxy holds billions of potentially habitable worlds by current estimates, each a possible foothold for such expansion. Across a species old enough to remember Earth only as a distant origin, the galaxy itself could become just another home among many. Genetic drift behaves differently once humanity spreads across many worlds. Populations settling on different planets encounter different gravity, radiation, and light, and natural selection answers each pressure in its own way. Isolated for enough generations, such groups could diverge more than any two peoples on Earth have ever diverged. Geneticists studying isolated populations note that separation alone, sustained long enough, can produce distinct species. One humanity might gradually become several, each shaped by its own sky. Earth's biosphere has recovered fully from every extinction event in its deep past, and the present crisis need not be the exception. Given enough uninterrupted generations, forests could regrow, reefs could rebuild themselves piece by piece, and empty ecological niches could refill with new species shaped to fit them. Paleontologists studying past recoveries after mass extinctions note that diversity often returns richer than before, not merely restored. A planet freed from pressure has, again and again, found new ways to fill itself with life. The Hawaiian Islands ride atop a tectonic plate that carries them steadily northwest across the Pacific floor. This same conveyor motion has already built a chain of islands and seamounts stretching far behind today's archipelago. Given enough distance still to travel, the current islands could shift several hundred kilometers from where they now sit, cooling and wearing down as they go. New islands would rise behind them from the same volcanic hotspot, a chain that never truly stops growing. Volcanic hotspots beneath the ocean floor keep producing fresh land long after older islands have drifted away and worn down. A new island can rise above the waves, stand for a stretch, and then erode back beneath them within a few million years. Wind, rain, and gradual subsidence work on every young island, wearing peaks into reefs and reefs into shoals. The ocean floor keeps this rhythm going, building and dissolving land in a cycle that has repeated for eons. Human-engineered organisms could do more than survive on new worlds. They could reshape those worlds outright. Microbes built to process alien soil, plants bred to breathe unfamiliar air, and animals suited to unfamiliar gravity might together turn a barren planet into something closer to a living one. Synthetic biologists already design organisms for specific tasks, and future descendants could extend that craft toward entire biospheres. A single engineered ecosystem, released into the right conditions, might carry a whole planet toward life. Separated by light years, human settlements could drift apart, not only in body but in thought and speech. Without shared contact, dialects could turn into distinct languages within a handful of generations, and customs could evolve along paths no other colony would recognize. Linguists studying isolated communities on Earth have already watched this happen across mere centuries among small, cut-off populations. Multiplied across a galaxy and unshared histories, whole civilizations of human descent might grow as foreign to each other as any two nations are today. Breath moves through you now, without any effort of your own. Notice the inhale arrive, then let it fold into an exhale, a little longer than the one before. Each breath needs nowhere to go, and nothing to prove. With every release, your shoulders sink further into the mattress, your jaw loosens, and your thoughts drift like unhurried clouds without a destination. Just breathe, and let that rhythm carry you further into rest. The Mediterranean Sea sits where the African and European plates keep pressing closer together. This same collision that already raised mountain ranges along its shores could, given a similarly vast stretch, close the sea's basin entirely. What ships have crossed for ages could become dry land threaded with new mountain chains, born from the same slow crush that shaped the Alps. Geologists tracking this convergence describe it as one of the more certain long-range outcomes in Mediterranean geology. Atlantic seafloor keeps spreading outward from a ridge running down its center, pushing the Americas and Europe further apart each year. New crust forms along this ridge at roughly the pace fingernails grow, a pace too small to notice yet impossible to stop, continued across enough generations. This widening could carry entire continents far from where they began, opening more ocean between shores that once sat close together. The same restless ridge that built the Atlantic keeps building it still. Australia drifts north at a measured pace, closing the gap between itself and the islands of Southeast Asia. Within a stretch measured in tens of millions of years, this movement could bring the continent into contact with the Asian mainland, folding new mountains up where island chains and shallow seas now sit. Geophysicists tracking the Australian plate's northward path see this collision as a near certainty given enough distance still to travel. A single vast landmass could come to stretch from the Indian Ocean to the edges of the Pacific. One full circuit around the Milky Way's center takes our solar system roughly 230 million years to complete. Across the span these long ages now cover, Earth's system could travel through a significant portion of that circuit, drifting past new star-forming regions and passing through different spiral arms. Each stretch of that path exposes the Sun and its planets to unfamiliar neighborhoods of stars. The galaxy itself becomes a kind of calendar for measuring time this vast. Civilization able to capture the full energy output of its home star earns a place among what physicists call Kardashev Type II societies. Should humanity persist across these long stretches of time, harnessing the Sun's entire output might become achievable, perhaps through vast structures built around the star itself. Such power could fuel projects hard to picture today, relocating worlds, building habitats by the thousands, lighting entire star systems from a single source. Earth has weathered devastating asteroid strikes throughout its history, and nothing overhead promises a quiet future. Astronomers tracking near Earth objects note that further major impacts remain statistically probable across the immense span still ahead. A future strike, large enough to disturb the biosphere, could once again clear away entire branches of life. Such collisions, rare within a single lifetime, look almost routine when measured against deep planetary history. Whenever a mass extinction empties the world's ecological niches, life tends to refill them with forms suited to whatever remains. Should such an event occur again, paleontologists expect new megafauna could rise, taking on roles once held by animals long gone. Enormous grazers, unfamiliar predators, or creatures shaped by altered climates might spread across these open landscapes. Evolution rarely leaves empty ground unclaimed for long. Humanity's descendants, spreading star by star across many centuries, could in time chart every corner of the Milky Way galaxy. Such a survey would mean examining more than 100 billion stars and countless planets scattered among them. Every hidden nebula, every hushed stellar nursery might be catalogued and understood. A map this complete would stand among the most thorough surveys any civilization could ever attempt. Mountain ranges rise and wear away on timelines far longer than any single lifetime can register. The Andes and Himalayas, still pushed upward by colliding plates, could stand taller than they do now, or could have worn down through wind, ice, and rain across these long ages. Their fate depends on which force, uplift or erosion, wins across the passing millions of years. Either way, their peaks would resemble little of the postcards known today. Biological engineering, given deep enough mastery over genetics, might not stop at repairing or improving the human body. Geneticists speculate that entirely new forms of intelligent life could be designed from the ground up, built for environments no unmodified human could endure. Such creations might think, communicate, and sense the world in ways unlike our own. What began as medicine could end as the deliberate authorship of new minds. Let your weight settle fully into whatever is holding you right now. Notice your feet growing heavy first, sinking a little deeper into the mattress beneath them. That heaviness climbs upward, into your calves, your thighs, spreading through your hips until they feel planted, unmovable. Your arms follow, growing dense and warm at your sides. Let your chest sink too, your back pressing into the bed until your whole body feels held by the earth beneath it rather than lifted above it. Continents drift toward one another even now, tracing patterns that have played out many times across Earth's history. Geologists project that within about 250 million years, most land masses could fuse into a single supercontinent, sometimes called Pangaea Proxima. Oceans would narrow between colliding shores, while new mountain ranges rise along the seams. It would mark another turn in a cycle Earth has repeated since continents first began to wander. The moon drifts outward from Earth by a few centimeters every year, a retreat driven by the pull of ocean tides. As it moves farther away, its grip on Earth's spin weakens, stretching each day a little longer across the passing ages. What now takes 24 hours to complete could take noticeably more across these vast timescales. Distant descendants might live by a clock quite unlike the one shaping our days today. Tens of thousands of kilometers will stretch between Earth and its companion moon compared to the distance we know today. Centuries of gradual drift compound into something vast, pulling the moon into a wider, slower orbit. From that greater distance, it would hang smaller and paler in the night sky, its pull on the tides noticeably weaker. Eclipses that once aligned with perfect precision could no longer fit together in quite the way they do now. A future sky would carry a familiar shape, grown subtly distant. Oxygen levels in Earth's atmosphere could rise and fall considerably as plant life itself keeps transforming across the ages. Forests, grasslands, and ocean plankton all breathe oxygen into the air through photosynthesis, and their balance shifts as species decline and new ones take their place. Ancient Earth once held far more oxygen than it does now, and later eras held less. Future atmospheres may swing through similar highs and lows as living things keep reinventing how they grow. Every 100 million years, the sun brightens by roughly 1%, a pace too faint to notice within a single lifetime. This gradual increase comes from hydrogen slowly fusing into helium deep within its core, leaving it marginally hotter and denser with time. Across 1 billion years, that tiny creep compounds into something Earth cannot ignore, like grains of sand slowly filling a vast hourglass. Long before the sun becomes anything dramatic, its steady brightening alone will reshape the world beneath it. Ice ages and warm intervals will have swept across the planet, again and again, long before this story reaches its end. Earth's climate has always rocked between frozen and temperate extremes, driven by shifts in its orbit, its tilt, and the slow rearrangement of continents. Vast glaciers creep toward the equator before retreating toward the poles, only to advance once more in due time. Cold and warmth simply take turns holding the world, trading places across immeasurable stretches of time. Earth's biosphere may pass through several more complete rounds of collapse and renewal before this billion-year span concludes. Life on this planet has already survived at least 5 great extinctions, each one clearing space for entirely new lineages to rise. Paleobiologists studying these ancient patterns suspect the story is far from finished. Future upheavals, whether from impacts, volcanic outbursts, or drifting climates, could clear the stage again, and life has always shown a stubborn talent for filling whatever room is left behind. Human descendants, should any lineage of us persist that far, might exist as entirely post-biological beings. Flesh, bone, and blood may prove too fragile a foundation for a species hoping to outlast geological ages. Consciousness, memory, and identity could instead be carried in engineered substrates built to resist decay, radiation, and the passage of time itself. Whether such beings would still count as human remains an open question one biology alone cannot settle. Entire star systems could one day supply the energy needs of civilizations advanced enough to harness them fully. A star radiates more power in a single second than humanity has used across its entire recorded history combined. Civilizations capable of capturing even a modest fraction of that output could sustain undertakings unimaginable today. Physicist Nikolai Kardashev once ranked civilizations by exactly this measure, imagining societies that graduate from planetary power to something drawn directly from a star. Around the sun itself, distant engineers might one day construct sprawling lattices built purely to gather its light and warmth. Physicist Freeman Dyson once described structures of this kind, vast shells or swarms of collectors encircling a star to capture nearly all its output. Built from asteroids, moons, or disassembled planets, such a structure could power projects on a scale Earth alone could never sustain. No one yet knows whether any civilization, ours included, would ever choose this path. A low hum moves somewhere beyond this room, the kind of sound a house makes when it settles into night. It rises for a moment, then fades, like a breath drawn out and released without effort. Maybe it's wind, finding a gap in the window, or a furnace letting go of its last warmth before rest. It doesn't ask anything of you. Let it arrive, let it recede, and let your attention drift along beside it, with nowhere in particular it needs to land. Earth's crust could grow noticeably thinner after eons of relentless tectonic motion and steady internal cooling. Plate tectonics recycles crust as material sinks in some regions and rises in others, but that engine depends on heat rising from the planet's core. As the interior cools across hundreds of millions of years, that circulation gradually loses its strength. Thinner crust could mean fewer emerging mountains and diminished volcanic activity, a geological pulse once vigorous now drifting toward stillness. Sea levels could swing by hundreds of meters as long-term climate cycles rise and fall across ages. Ice ages lock water into growing ice sheets, pulling seas lower, while warm periods release that water and lift shorelines again. Across hundreds of millions of years, these swings could repeat many times over, redrawing every coastline the planet has ever known. Cities familiar today would be submerged or stranded far inland by these patient rhythms, already written into layered rock as proof of cycles long past. Solar flares could grow more dangerous to civilizations that lean ever further into technology. As societies depend more on satellites, power grids, and delicate electronics, a single powerful flare could disrupt communication across whole continents at once. The Carrington event of 1859 offers a small preview of what a major flare can do to a wired world. Civilizations spread across many worlds might need shielding far beyond anything built today, since the sun's ancient outbursts could matter more, not less, as dependence deepens. Instantaneous communication across interstellar distances might one day become possible for humanity's descendants. Physics as understood today forbids information from outrunning light, though theoretical work on quantum entanglement continues to be studied without yet revealing a way around that limit. If some future breakthrough ever bent this rule, colonies scattered across star systems could speak without the centuries of delay light imposes. Whether such a discovery lies ahead remains an open question no one can yet answer. Artificial ecosystems on distant worlds could one day replace Earth altogether as humanity's home. Engineered biospheres, sealed habitats, and terraformed surfaces could offer conditions gentler than an aging homeworld ever could. Descendants born inside these constructed worlds might never set foot on Earth, knowing it only through records and stories carried forward. Earth could remain a place of origin rather than residence, honored but no longer needed, while home simply becomes wherever life can still be sustained. Certain lineages of humanity's descendants might no longer look human at all. Generations shaped by different gravities, radiation levels, and atmospheres could drift into physical forms suited to their worlds. Skin, bone density, limb proportions, even senses could shift to match environments Earth never offered its children. A visitor from today might struggle to recognize such descendants as kin, though their ancestry would trace directly back to this planet. Evolution, over such spans, tends toward whatever survives best. Self-replicating robotic probes could have spread across the entire observable galaxy. This idea, first explored by mathematician John von Neumann, describes machines capable of building copies of themselves from raw material found among asteroids and moons. Launched even at modest speeds, such probes could theoretically fill the galaxy within a few million years, a blink beside a billion. Whether humanity would ever choose this path, or whether such machines already drift unnoticed somewhere out there, remains unresolved. After it forms, even a supercontinent eventually breaks apart again. Earth's plates have assembled and scattered continents many times across its history, and nothing suggests this rhythm will ever stop for good. Following the formation of a future supercontinent, heat rising from below would again crack it into new fragments over tens of millions of years. New oceans would open where rifts widen, and new mountain ranges would rise where fragments collide once more, the map of the world endlessly rewritten. Within 600 million years, carbon dioxide could fall too low for most plants to survive. As the sun brightens, weathering of exposed rock speeds up, pulling this gas from the atmosphere faster than volcanoes can replace it. Most plants rely on a minimum concentration to carry out photosynthesis, and dropping below that threshold would starve the process at its root. Forests and grasslands could thin and vanish long before oceans ever begin to boil, life-bound to plants facing this quieter ending first. Between 600 and 800 million years from now, the sun's brightening light could start boiling away Earth's oceans. As solar output climbs by about 1% every 100 million years, surface temperatures would eventually cross a point where water evaporates faster than rain can return it. Water vapor itself traps heat, feeding a runaway effect once it begins in earnest. Oceans that have covered most of the planet since its youth would start shrinking toward this transformation's edge, one of the surest endings Earth's living world will ever face. Let a low heat begin at your feet, as if resting near embers that ask nothing of you. Let it climb the ankles, the calves, the knees, spreading upward without hurry. Feel it settle into your hips, your stomach, easing whatever small tightness it finds along the way. Let it rise through your chest and shoulders, down through your arms until your fingers loosen one by one. Let it reach your neck, your jaw, the space behind your eyes, until your whole body rests inside this glow, heavy and unbothered, ready for sleep. 800 million years from now, complex life as we know it may no longer be possible on Earth's surface. Rising heat and falling carbon dioxide would combine to strip away the conditions that plants, animals, and ecosystems depend upon. Forests would have vanished long before this point, leaving little to sustain oxygen-breathing creatures. What endures, if anything, would need to survive in forms utterly unlike the life alive today. Earth's surface temperature could climb past the point where unmodified humans might endure. Heat radiating from a brighter sun would push average conditions into territory the human body was never built to handle. Skin, lungs, and circulation all depend on a narrow thermal range that this future would erase. Any descendants remaining on Earth by then would need bodies reshaped for a harsher world. Plate tectonics could begin slowing as the planet's molten interior continues losing heat. Convection currents deep below the crust have driven continents apart and together for billions of years. But that engine runs on a finite supply of warmth. As the core cools, the plates above it would move less and less. Mountains would rise more rarely, and the restless shifting of the map would gradually still. Volcanic activity could decrease significantly as the forces beneath the crust weaken. Fewer eruptions would mean less carbon dioxide released back into the atmosphere, breaking a balance life has relied upon for eons. Volcanoes have long served as a slow thermostat, replenishing the very gas that weathering and photosynthesis pull away. Without that steady contribution, the planet's chemistry would settle into a quieter, more stagnant equilibrium. The atmosphere, no longer replenished by living things, could lose most of its free oxygen. Photosynthesis has kept this gas abundant for over 2 billion years, but a biosphere in decline could no longer keep pace with the ways oxygen naturally disappears through rust and chemical reactions. Air that once supported vast forests and animal life would grow thin in this one vital ingredient. The sky above Earth would look the same, yet breathe entirely differently. If humanity still exists by this era, it may have already left Earth behind for artificial homes among the stars. Space stations, hollowed asteroids, and rotating habitats could offer more livable space than the dying planet below. Such structures would let their builders control temperature, gravity, and air with total precision. Earth, once the only cradle of humankind, might become just one address among countless others. Far beyond Earth, terraformed exoplanets could serve as new homeworlds for humanity's descendants. Engineers of some future era might have seeded distant worlds with atmosphere, water, and life carefully chosen to thrive there. Such planets would carry echoes of Earth in their forests and oceans, yet remain entirely their own. Each newly living world would stand as a quiet monument to a species that refused to end with its birthplace. Whole moons and asteroids could be relocated by advanced civilizations seeking resources or living space. Nudging such bodies into new orbits using gravity and patient thrust rather than force is a feat that remains within the reach of physics, if not of any near timeline. Hollowed from within, an asteroid could become a traveling habitat carrying its own soil, water, and sky. Entire worlds, once fixed points, could become movable pieces on a much larger board. Great structures in orbit could one day shield Earth from a sun growing steadily more intense. Vast sunshades, positioned at a stable point between planet and star, might scatter or filter incoming light before it ever reaches the surface. Such megastructures would need materials and engineering far beyond anything built so far. Whether builders would choose to save Earth this way remains an open question, one no one alive today can answer. Deep in the vacuum of space, human biology could be reshaped to withstand radiation levels no unmodified body could survive. Deep space travel exposes living cells to cosmic rays, far beyond what Earth's atmosphere and magnetic field normally block. Genetic engineering might grant future descendants natural resistance, repairing damage as quickly as it occurs. A body built for the stars would carry little resemblance to the fragile flesh that first left Earth. Dust hangs in a shaft of still air, each speck barely moving, suspended in a fall of light that never quite finishes. Nothing asks it to settle, nothing asks it to rise. It simply remains, weightless, unhurried by any clock in the room. Let your own thoughts do the same. Small motes of the day held in place, in no rush to land anywhere at all. Your breath finds that same unhurried rhythm now, rising and settling, again and again, needing nothing from you but to continue. Nearby stars will have completed several more circuits around the galaxy's core by this point in time. Each such journey, a single galactic year, takes roughly 230 million years to complete. Over 1 billion years, the Sun and its neighbors will have swept around the galactic center 4 or 5 times. Familiar constellations, built from stars now scattered along different paths, would have long since dissolved into new, unrecognizable patterns overhead. Supernovae among nearby stars could have detonated more than once across such an immense span of time. Each explosion sends a shockwave of enriched gas and dust rushing outward, altering the density and chemistry of nearby space. Some of those shells of material might have swept past the solar system's former neighborhood, seeding new pockets of gas with heavier elements. Local interstellar conditions, once familiar, would feel entirely different by the time 1 billion years had passed. The Milky Way's spiral arms will have swept past the solar system's old position many times over during 1 billion years. Stars, gas, and dust move through these arms like traffic through a slow turning intersection, entering dense lanes of star formation and then drifting free again. Whatever region once cradled Earth's sun would have long since fallen behind, replaced by unfamiliar arms and unfamiliar light. The galaxy itself, vast and unhurried, keeps rearranging its own architecture across these enormous stretches of time. Human civilizations, spread wide enough across time, could have found and settled thousands of exoplanets by now. Each world would offer its own gravity, its own sky, its own particular chemistry to adapt to. Some might resemble Earth closely enough for unmodified descendants to walk freely outdoors. Others would demand engineered bodies or sealed habitats. Across so many worlds, the very idea of a single human homeland would have quietly dissolved into something far larger. Interstellar communication networks could stretch across much of the Milky Way by this era, linking scattered human settlements. Signals sent at the speed of light would still take centuries or millennia to cross such distances, turning every exchange into something closer to letter, writing across deep time. Relay stations, built at intervals among the stars, might carry messages onward long after their original senders have died. Whole civilizations could trade knowledge this way, across a silence that language alone had learned to bridge. Some human descendant species could have merged so completely with artificial intelligence that biology and code become indistinguishable. Thought, memory, and awareness might transfer freely between organic tissue and synthetic substrate, with no clear line marking where one ends and the other begins. Such beings could experience time differently, compressing centuries into subjective moments or stretching seconds into vast internal deliberation. Whether this counts as a continuation of humanity or the beginning of something else remains an open question. Earth could become a preserved monument to history rather than a living, breathing home. Descendant civilizations scattered among the stars might return here only as visitors, walking through carefully maintained ruins and reconstructed landscapes. Museums built across whole continents could hold the record of everything humanity once was, tended by caretakers rather than crowded by residents. The birthplace of a species would remain, in this telling, cherished but empty, more archive than address. Human genetic archives, stored deep and cold, could preserve the original genome for billions of years without decay. Vaults carved into asteroids or buried beneath planetary crusts might hold every strand of information that ever made a human body human. Even if descendants had changed beyond recognition, this archive would keep the starting point intact, available to be read again. A single sequence, unmoving in the dark, could outlast every civilization that once copied it. Oceans across Earth could evaporate away entirely within about 1 billion years, as the sun's slowly intensifying heat overwhelms the planet's water cycle. What began as gradual warming would eventually boil away every remaining lake, sea, and ice sheet, leaving dry basins where water once pooled for eons. Water vapor lifted into the upper atmosphere would break apart under sunlight, its hydrogen escaping into space and never returning. The blue world visible from orbit today would by then have turned entirely dry. Surface temperatures across Earth could rise past 100 degrees Celsius within 1 billion years. The sun's brightening output would pour more heat onto the planet than any remaining water cycle could release. Rock and dust would bake under skies stripped of moisture, and stone once cooled to the touch would hold heat long after nightfall. Geologists studying stellar aging describe this as an almost inevitable stage in a planet's long relationship with its star. Let the jaw soften now, just slightly, the way it does when a thought finally finishes itself. Let the muscles around your eyes loosen, unclenching from wherever the day left them. Behind closed eyelids, the dark deepens, wide and unmarked, asking for nothing at all. Let your face rest the way still water rests, holding no shape but its own. Polar ice caps at both ends of Earth could vanish completely within this same billion-year stretch. The white regions that once reflected sunlight back into space would give way to bare rock and dark soil, absorbing heat rather than deflecting it. Without ice to cool the poles, the planet would lose one of its oldest thermostats. Climate scientists studying planetary aging note that this loss alone would accelerate every other change already underway. Plate tectonics could grind to a stop somewhere between 1 billion and 1.5 billion years ahead. As Earth's interior continues cooling, the molten rock driving continents apart would lose its churn, and the plates would settle into stillness. Mountains would stop rising, and ocean trenches would stop swallowing crust. Planetary scientists regard this shutdown as one of the surest signs that a world has entered its geological old age. Cooling steadily at the planet's center, Earth's molten core could lose the churn that generates a magnetic field. As that inner motion fades, the invisible shield surrounding the planet would grow fainter with each passing age. Such weakening follows the same physics already observed on smaller, cooler worlds like Mars and Mercury. A field once strong enough to guide compasses could fade into something barely detectable. A weakened magnetic field would leave the atmosphere exposed to the endless push of solar wind. Charged particles streaming from the sun, once deflected safely around the planet, could instead strike the upper air directly, stripping it away molecule by molecule. Over vast stretches, this thinning would leave the sky lighter, drier, and less able to hold heat or moisture. Researchers studying atmospheric loss on other worlds see this same process already written into the thin air of Mars. Earth could come to resemble present-day Mars in nearly every geological sense within 1 billion years. A thin, stripped atmosphere, a cooled and quiet core, dry basins where oceans once moved. Red dust might settle across surfaces once green, and wind alone would carve what water no longer could. The two worlds, so different across the ages of the solar system, could finally converge into a shared kind of stillness. The last extremophile organisms on Earth could survive only in refuges deep beneath the surface. Microbes tolerant of heat, salt, and radiation might persist in cracks of rock, fed by chemical reactions rather than sunlight long since grown too harsh above. These hidden pockets, cool and mineral-rich, could hold on to life long after the surface world had gone silent. Biologists studying such organisms today already find them thriving in places sunlight never reaches. Humanity, if it endures this long, would likely have left Earth behind altogether. The conditions that once cradled every human generation would no longer support unmodified life of any kind. Descendants scattered among orbital habitats, distant moons, and terraformed worlds might look back on this planet only through recorded images. The home that shaped an entire species could become, by then, simply the place a species used to be. By this point, human civilization could exist primarily among the stars, rather than anchored to any single world. Generations born aboard habitats, stations, and slow-moving arcs might never set foot on a planet at all, and space itself would feel less like a frontier and more like home. Identity as a species would stretch across countless small worlds of metal and light, none of them irreplaceable. What once required a single blue planet could, given enough distance, need nothing but each other. Rotating habitats, built to sustain entire generations, could become home to most of humanity's descendants. Vast cylinders spinning through the dark might generate their own gravity, their own light, their own weather systems in miniature. Families could be born, grow old, and pass on inside walls that never touch a planet's surface. Earth, in such a future, might become one home among countless engineered ones, no longer the only place a person could begin. Entire biospheres, forests, coral systems, whole webs of interdependent species could be lifted from a failing world and settled on another. Engineering on this scale would mean transporting soil microbiomes alongside root systems, insects alongside pollinators, so an ecosystem arrives intact rather than fragmented. A newly hospitable planet might, within centuries, host jungles indistinguishable from ones that once grew on Earth. Such transplantation would carry across not just species, but the intricate relationships between them. Let your breath find its own rhythm now, without any effort to guide it. Notice the small pause at the top of each inhale and the longer, looser release that follows. Each exhale can grow a little longer than the one before, like a tide easing further back with every pass. There is no pace to keep, no counting required, only the body's old rhythm doing what it has always known how to do. Let it carry you further down, breath by breath. Bones and muscles, freed from a planet's pull, could evolve along different lines entirely. Generations raised in orbit might develop longer limbs, redistributed fluid systems, and different patterns of balance and inner ear function. Without gravity's constant tug, some human descendants could simply thrive rather than merely endure. Life spent tumbling gracefully through open modules might feel to them no stranger than walking felt to their ancestors below. Inside habitats built far from any star, fusion reactors could take on the role sunlight once played. Engineered cores might glow with a steady, adjustable brightness, cycling through day and night on a schedule chosen by their inhabitants rather than dictated by orbit. Crops could grow under this manufactured glow, just as readily as under any distant sun. For colonies drifting between star systems, this small captured fire could become the only sky they would need. For a portion of humanity's descendants, mind could part entirely from body. Neural patterns, copied and sustained inside vast computational substrates, might carry memory, personality, and thought without any biological form to house them. Such minds could experience decades of subjective life within moments of outside time, or slow themselves to match the pace of distant stars. Whether this counts as survival or something else entirely remains an open question, one still unanswered even in principle. Aboard slow-moving arcs crossing the dark between stars, samples of Earth's biodiversity could be kept intact indefinitely. Seed banks, frozen embryos, and cultured cell lines might travel for centuries without needing to touch soil. Whole ecosystems, held in careful stasis, could wait for a planet ready to receive them again. In this way, a single ship might carry forward the accumulated variety of billions of years of evolution. A terraformed Mars, thickened with a new atmosphere and warmed over centuries, could stand ready as a second homeworld by this point. Engineered greenhouse gases and imported ice might have given the planet rivers, clouds, and breathable air once again. Descendants could walk its surface without suits, under a sky turned faintly blue instead of rust-colored. For a species already scattered far beyond it, Mars might simply become one more familiar address among many. Out of clouds of gas and dust, entirely new planets could be assembled by design rather than by chance. Engineers on this scale might gather raw stellar material, compress it, and shape it into worlds, built precisely for the life meant to live there. Such planets could be given exact gravity, exact axial tilt, exact atmospheric mixtures, tailored from the very beginning. What once took a star system billions of years to form randomly could by then take mere generations to build on purpose. Given 1 billion years, distance itself would cease to be much of a barrier. Colonization fleets, launched across countless generations, could cross not only the Milky Way but drift onward into neighboring galaxies entirely. Andromeda, visible tonight as a faint smudge of light, might by then hold outposts of human descendants, gazing back toward a home galaxy grown unfamiliar. Across such spans of time, even the word far would need a new definition. Not every branch of humanity would need to change. On certain worlds, or perhaps on Earth itself, some communities might choose to stay close to the biology their ancestors carried. Stable environments, careful stewardship, and plain preference could keep a population looking and living much as we do now. Even amid galaxies full of altered descendants, an original kind of human could persist, one steady thread among countless others. Control over a star's own life cycle could become an ordinary technological skill. Advanced civilizations, given enough energy and enough time, might learn to adjust how a star burns, how long it shines, even how it eventually dies. Stellar evolution, once governed only by mass and physics, could become something engineers shape on purpose. A star might be nudged to burn slower, brighter, or longer, tailored to the needs of the life depending on it. Around a dying star, engineered life might still find a way to survive. Human descendants, wherever they had gone, could design organisms and habitats able to draw warmth from cooling embers rather than a healthy sun. Even a dead star, a dark stellar remnant, might still offer enough residual heat or gravity to sustain a colony. Life first evolved to depend on sunlight, but by then it might no longer need it at all. Feel the mattress take the full weight of your body now. Let your shoulders sink first, then your arms heavy against the sheets. Your legs grow dense, as though gravity had doubled just for tonight. The back of your head presses deeper into the pillow, no muscle asked to hold anything up. There is only weight now, drifting downward, settling into stillness, sinking further into the dark below you. Rather than only orbiting a star, an advanced civilization might rebuild its entire surroundings into a machine built for motion or energy. Vast mirrors, shells, or asymmetric structures could push a star and everything bound to it gradually across the galaxy. Engineers have sketched such designs for decades, giving a star system the ability to travel like a slow, deliberate vessel. Entire worlds could ride along, carried by their own sun. A star's lifespan could be stretched far beyond its natural course. By slowing the rate at which it burns through fuel, careful engineering might delay the moment it finally dims and dies, removing excess mass, redistributing hydrogen, or shielding a star's core could each extend its useful years by billions. A civilization willing to attempt this could effectively choose how long its own sun continues to shine. The sun will have burned through only a small additional fraction of its hydrogen fuel. Even after 1 billion years, our star would still sit well within its long main sequence life, a middle-aged sun continuing its steady burn, compared to the 10 billion years it has to spend as a stable, hydrogen-fusing star. 1 billion years is a modest chapter. The sun, in other words, would barely have aged, even as everything living near it changed beyond recognition. Left untouched, Earth's biosphere would not survive 1 billion years. Without deliberate intervention, rising temperatures, evaporating oceans, and a thinning atmosphere would eventually erase every form of unmodified life the planet once held. Forests, oceans, insects, and animals, the entire familiar web of biology, would have nowhere left to hold on. The Earth that gave rise to humanity would by then be silent in the way old, spent worlds are silent. Only life that had been engineered or carried elsewhere could still speak for humanity's legacy. By this point, whatever remained of the human story would live in colonies, arcs, and altered biology far from the original planet. Earth itself, empty of its old life, could no longer hold that inheritance alone. The story once written in forests and coastlines would continue instead in habitats, genomes, and memories carried across the stars. Surviving 1 billion years would place human civilization far beyond any species known to science. Most species on Earth last a few million years before evolving into something else or disappearing entirely. A civilization enduring 1,000 times longer than that would represent something unprecedented in the fossil record, on this planet or, as far as we know, anywhere else. Whatever humanity became by then, its sheer duration alone would make it something the universe had rarely, if ever, produced. 1 billion years of continuous change would leave little of the original human form intact. Bodies adapted to different gravities, radiation levels, and atmospheres would diverge in ways early humans never anticipated. Descendants scattered among distant stars might vary from one another as much as they would from their ancestors on Earth. What once meant human could stretch to include shapes, sizes, and biologies barely imaginable today. The Milky Way galaxy would complete roughly 4 full rotations within that same billion years. Each turn around the galactic center takes around 225 million years, carrying the solar system through different neighborhoods of stars and dust. 4 such circuits would mean 4 long journeys through the spiral arms and back again. The galaxy itself would look much the same, even as everything living within it transformed completely. Energy drawn from many star systems at once could, in theory, power a civilization that old. Instead of depending on a single sun, such a species might link the light of dozens or hundreds of stars into one shared supply. Structures built for that purpose could stretch across light years, quietly gathering power from every direction. A civilization capable of this would treat entire star clusters the way earlier humans once treated a single river or coastline. Biological life itself might come to mean something different by then. Descendants shaped by genetic design, merged with machinery, or rebuilt from digital patterns, could blur every boundary that once separated the living from the artificial. What counts as a body, a mind, or a species could shift with each new generation. The definitions that once felt fixed might become one chapter in a much longer story. Somewhere beyond the window, a low hum rises and fades, the way an old house breathes as the dark deepens. It doesn't ask anything of you. It only arrives, holds a moment, then eases back into silence, like a tide that turns without hurry. Let each return of that hum settle your shoulders deeper into the mattress. There's nothing to follow, nothing to name, just this hushed coming and going, again and again, until your breath falls into its rhythm. The word human could become less a biological category and more a marker of history, Future beings tracing their lineage back to Earth might use it the way people today use the word ancestor, pointing toward origin rather than describing a body. What began as a species designation could settle into something closer to a shared memory. Being human, by then, might mean belonging to a story rather than sharing a genome. In the search for civilizations beyond Earth, humanity's own long survival could become the clearest example anyone has to study. Researchers searching for signs of other advanced species often wonder what a long-lived technological civilization would look like. A billion-year human story, if it happened, would answer that question through its own existence. It would show, in real detail, what patience and adaptation can build across almost unimaginable stretches of years. Complex multicellular life on Earth has existed for a little over 500 million years, and even that falls short of 1 billion years of human survival. Before that, life stayed simple for eons, single cells suspended in ancient seas, long before anything resembling a body appeared. 1 billion years of human history would then outlast the entire visible record of complex life on this planet. It would be, in a very real sense, a second creation story layered on top of the first. Few civilizations, real or imagined, could match 1 billion years of continuous survival. Even the longest-lived species in Earth's fossil record rarely persisted beyond a few million years before changing into something else entirely. 1 billion years would place humanity not just among the long-lived, but among the longest-lived possibilities conceivable in any known history. It would be a kind of endurance that borders on what evolution or imagination usually allows. In 1964, the astronomer Nikolai Kardashev proposed a scale for measuring how much energy a civilization could command, with its highest tier describing power drawn from an entire galaxy. 1 billion years of growth, expansion, and engineering might be exactly what it takes to reach that scale. Harnessing countless stars, reshaping matter, and spreading across galactic distances would no longer be theoretical at that point. It would be what humanity by then had become. Set beside the sun's full lifespan, 1 billion years of human survival would still look modest. The sun burns for about 10 billion years in total, and even a full billion years of human endurance would fill only 1/10 of that story. Stars measure time in spans human minds can barely hold, and against that backdrop, even remarkable persistence remains a single chapter, not the whole book. Most known species leave a fossil trace lasting only a few million years before nature reshapes them into something new. 1 billion years of human survival would stretch far beyond that, longer than almost any story written in stone. Whatever shape humanity might take by then, woven into starlight, drifting among distant suns, or simply resting in a warm bed tonight, the thread connecting it all begins here, in this hushed moment of rest. Sleep now, unhurried through the dark.